Okay, so today we're talking about Chapter 3, Section 2, Polynomial Functions and their Graphs. Okay, so we've talked about parent functions and transformations of functions, but there's also other parts of functions that we need to talk about, and that just basically be, their behavior, right? So first of all, let's talk about the definition of a polynomial function. Right, so the definition, all right, and this is a very rigorous definition, and honestly, it's a definition that you probably don't really care about, and you definitely won't use unless you're going into mathematics, right? But that's not to say that it's not useful. But the definition of a polynomial function: if let n be a non-negative integer, and let a sub n minus 1, all the way to a sub 0 be real numbers, right? We're just basically saying they're numbers, all right? And n is not equal to 0, because I'm sorry, a sub n is not equal to 0, then the function defined by f of x equal to, and notice how it's a sub n times x to the nth power plus a sub n minus 1 times x to n plus minus 1 power, and we go all the way down to a sub 0. Okay, so sorry, that's a mouthful. It's called a polynomial function of degree n. Right, the number a sub n is a coefficient of the variable of the highest power. It's called the leading coefficient. Okay, so again, that's just a very rigorous definition. It's a definition that isn't necessarily, I don't know, needed or used so much in this particular course. And the graphs of polynomial functions, they are characterized by smooth continuous graphs. Right, so notice how these are all nice and smooth and they're continuous graphs, right? So an example of something that's not smooth is this. We have our sharp corners. Okay, and of course these are continuous, right? There's no breaks in the graph. Well, an example of a break in the graph would be this, right? Notice how we jump from one part of the graph and then we jump to the other part of the graph. Okay, so characteristics of a polynomial function is that they are smooth and continuous. The first thing we're going to talk about is the end behavior of our polynomial functions. All right, so the end behavior is just basically what happens at the extremes. Okay, so what happens when we go to negative infinity and what happens when we go to positive infinity. Now, there's another thing that you need to memorize, as well as we're going to talk about something called multiplicity today. It's a long word. It's a word you probably had never heard of, but it's a pretty simple concept. But the first thing we're going to talk about is end behavior. So this seems like a lot of information here, okay? But bear with me real quickly. So, and let's actually move this to the side and just kind of think about what we've done before. Okay, so I have spoken in the past about parent functions. Okay. So if we have x squared, right, a quadratic equation, we know as the graph, well, probably shouldn't put an equal sign. We know that the graph looks something like that, right? And we know that x cubed, well, that looks something like this, right? They're just rough sketches, rough drawings, but these are the end behaviors. I'm sorry, these are the graphs of those parent functions. Alrighty. Well, x squared is a parabola that looks like this. Well, so does x to the fourth. Okay, x to the fourth. Let's make it blue. Just kind of overwrite it. It looks like that, but it's a little steeper. And then x to the sixth. All right, so let's erase that blue there. X to the sixth would be even steeper. Okay, but the whole point of this is that the end behavior, what happens right here at the ends of the graph, it's the same, all right? And the end behavior is basically up, right? X squared, x fourth, x sixth, x eighth, well, not 9. Oh, I messed up there. X10, x12, all right? They all have that end behavior of going up and up. Okay? Well, now what if I had a negative x squared? Okay, well, we know that if we take the negative of that function, then we're going to be flipping it across the x-axis, right? Oh, that's not what I wanted. Eraser. All right, there we go. So if we're flipping across the x-axis, then we have a parabola that looks something like this, and so the end behavior changes from up to down. Okay, and that's the gist of it. If the exponent is even, right? If it is just simply a positive, if it's a positive even, if it's a positive even polynomial, then it will be up up. Okay, but if it is a negative, negative like this, then it's gonna be down down. Alrighty, so let's erase that real fast. Well, yeah. All right, that takes care of if we have an even uh, uh, exponent. Oh, that's the word I forgot to say. Exponent. Okay. If we have an odd exponent, all right, well, x cubed we know behaves something like this, and we would say something along the lines of, it's down up. Okay. Now we'll be more precise, considering. Well, I don't know if we actually do in this textbook. Okay. Well, it looks like for now we'll stick with the ups and downs. Okay. All right, so when it's x cubed, it's down up, right? Well, if it's a negative x cubed, a negative, then we just basically, again, we flip it across the x-axis, and then the end behavior is up, down. Okay, so all we're talking about is the end behavior of our polynomials at the extremes, all right, as we go to negative infinity and as we go to positive infinity. All right? And so, again, that's just kind of the crash course. It really depends on if you took my advice and memorized those parent functions or not. Which, by the way, if you don't have them memorized, now's a really good time to get them memorized. Not only that, but there's for test 2. But anyways, that's basically what this chart's saying. Okay, so that was the kind of broken down definition. The more rigorous would be what we see here. Okay, so for n odd, so basically if my exponent is odd, well, if it's just a simple odd exponent, all right, it's going to behave like an x cubed. Okay, it doesn't matter what's in the middle. It does not matter what's in the middle. We're simply talking about the end behaviors, what happens down here and what happens up here. Okay, well, if it is a negative polynomial with an odd exponent. Sorry, all these words. If it is a negative polynomial with an odd exponent, then we flip it. Okay. So again, this behaves like our x cubed, and this is just our x cubed flipped across the x-axis. Well, if our exponent is even, all right, if it's even, our polynomial is a positive polynomial, then we just simply go like this. Right? It doesn't matter what happens in the middle. We see that we rise and rise. And then, of course, if it is a negative number, then we fall and fall. Right? So let's look at some examples. We might could fit a couple of these on here, honestly. Let's see. Let's just go see if example 3 can fit on here. No, we'll stick with those two. Okay, so example 1, use the leading coefficient test to determine the end behavior of the graph. Alrighty, so looking at example 1, all right, this polynomial, all right, well, looking at the very first one, okay, oh, by the way, I probably should have said that, I'm sorry. If you have these polynomials, you write them in descending order. That was, again, our definition of a polynomial. And we're looking at the very first polynomial, or the very first exponent, okay? Is it even or odd? That's what you're going to ask yourself. Is it even or odd? Well, this is an odd polynomial, or an odd exponent, okay? Well, if it's an odd exponent, we know that it's going to behave something like this, okay? The next thing we're going to do is we're going to look to see if the sign at the front is a positive or negative, okay? Well, there is no negative sign, so therefore it must be positive, right? So the end behavior of this function is going to be down up, right? It's going to be down, and it's going to go to up. And let's show you the actual what the graph looks like. And this is it. It's just simply, again, down up. At this point, we don't really care what's in the middle. We will later on in the section, but we don't really care what's in the middle here right now. Okay, we're simply talking about what happens right here at the extremes. Okay. Example 2 looks a little confusing, right? Well, you don't have to actually you don't have to actually foil, well, wrong color. You don't have to foil this out and all that stuff, right? Instead, what you're going to do is you're just going to count your exponents. Okay? So what you're going to say is, okay, you have an x cubed, that's 3. There's a squared there, and there's an implied 1 there. You'd say 3 plus 2 plus 1 is 6. Okay, so this is a 6th degree polynomial. 6th degree polynomial. 6th degree. Okay, so it's a 6th degree polynomial, so that tells me that my exponent is even. So I would expect an end behavior to be something like up, up. Okay, but we're going to look at this sign there. Okay, well, it's a negative sign. So that tells me that it's going to be flipped across the x-axis. So it's not going to be up, up. It's going to be down, down. It's going to be down, down. Okay. And again, right now we're not really concerned what's in the middle just yet. But we see that it does indeed. Do we not have the graph? Okay, well, we don't have the graph. But you can graph this and tell that it is indeed down, down, and we see that at least in textbook. In case you don't want to take my word for it, it is indeed down, down. Alrighty, so this is a pretty long example to just kind of get to the end behavior part, but we'll still discuss it. So example 3 reads, AIDS, HIV, remains a persistent problem for the United States and countries around the world. According to the CDC, at the end of 2020, an estimated 1.2 million people in the U.S. had AIDS. Using a limited portion of the data shown by the bar graph, we developed a model, this polynomial here, for the number of Americans with AIDS, f of x, x years after 1983. Use end behavior to explain why this model is only appropriate for a limited time period. Okay, so I guess this is more than end behavior, but let's discuss the end behavior for right now. So if we were to look at the end behavior, let's just look at the function here. Okay, so it looks like we have a 3rd degree polynomial, so that means that we're going to have some sort of end behavior that's either going to be down up or up down. Okay, so we see that's a negative there, so we can see that the end behavior is going to be this one, the up down. Okay, because again, this is x cubed ish, and this is the negative x cubed. Again, we just flip it across the x-axis, and these are just rough drawings. I know, I'm sorry, but if we're just talking about in behavior, there's really no precision involved here. Okay, so by looking at the in behavior of this graph, we see that we are decreasing without bounds over time. All right, so we are we have to look at this graph in a certain time period, because otherwise, we'd have a negative, amount of people with AIDS, which obviously does not make sense, right? But anyways, I guess that's where a textbook was going with this. Not entirely sure, but it is what it is. Alrighty. But anyways, that's that. Alright, so more of the same here. Alright, so this reads, the graph of f of x is equal to negative x to the 4th power plus 8x cubed plus 4x squared plus 2 was obtained with a graphing utility using a viewing rectangle. Okay, the graph is shown in figure 3.16. Let's check out figure 3.16. Is this a complete graph that shows the end behavior of the function? Okay, so if we were to look at this particular graph and ask ourselves, is this a complete picture, right? Well, we would actually need we would need more to the graph. So the answer would be no by looking at just this viewing rectangle. And I know that the authors of this textbook are more in tune with math education than I am, but I'm not entirely sure why this would be thrown in there. Besides, I mean, I guess I can see uh, showing that seeing the viewing rectangle is more important. Not just seeing the viewing rectangle, seeing the whole picture rather, okay? So to recap, because I do ramble a lot and I'm really sorry, we have our function here. It's a negative x to the fourth power, okay? Well, first of all, we know that this graph is not indicative of this particular function because this graph behaves, it looks like it's behaving like an odd exponent, right? The down up. It's behaving like an odd exponent. Whereas we know, looking at this particular function, that it is an even exponent, and it's a negative out front. So instead of being up, up, it'll be down, down. Of course, we see that here. So again, there's really no point in, I don't feel like there's any point in viewing this rectangle because obviously we know the end behavior without even looking at a graph, right? Or at least that's what we presume, and we would be right. Right? So we don't necessarily have to look at a graphing utility to tell the end behavior here is down, down. All right, so 0 is a polynomial. So now we're going to get to the part where I'm doing a lot less snipping and laser pointing and actually doing some computation. So the first few examples, we were just concerned with the end behavior of a function. Now we're going to figure out what happens in the middle. So previously, I said when we looked at these functions, we're just concerned about the end behavior here. What happens when we go off to the infinities? And I said we don't care what happens in the middle yet. Okay. Well, now we're about to care what happens in the middle. All right. We're going to care what happens in the middle, and we have to do all that. Unfortunately, we have to do it algebraically. So starting with example 5, it reads find all zeros. So how do I find zeros of a polynomial? Well, I set the polynomial equal to 0. All right, so once I set the polynomial equal to 0, and I solve for x. Now looking at this particular function, it is not a function that we are, accustomed to. Accustomed to being something that we can factor easily, a quadratic function that we can use a quadratic equation on. It's not one of those easier ones that we're familiar with. But here's a rule for you. For this class, well, shoot, you know what? For all the classes, for pre-cal, for this class, pre-cal, calculus, if you see 4 terms, okay, so 4 terms, 1, 2, 3, 4. If you see 4 terms, the first thing you need to think immediately is we're going to factor by grouping. So what is factor by grouping? So let's go ahead and write this function out. All right, so I'm going to write the whole thing out, and then I'm going to change some stuff. Okay, so this is just simply the function rewritten. We know that the notation f of x and y, they're pretty interchangeable. All right, so we can change this to a y. Okay. Now, if I want to find the zeros, I need to set y equal to 0. Okay, so I'm going to set y equal to 0. And let's move it off to the left so I can have some more room here. Here we go. All right, so now what I'm going to do is I'm going to solve this for x. So what I'm telling you now, if you see 4 terms, 1, 2, 3, 4, and again, terms are separated by addition and subtraction. Okay? If you see 4 terms, the first thing you need to think every single time, not just this class, but all your math classes moving forward, the first thing you need to think is factor by grouping. So what you're going to do is you're going to split it down the middle. Okay? You're just going to put 2 terms on the left, 2 terms on the right. Now, it's not always going to work out perfectly first time, but it will eventually. Okay? So what we're going to do is we're going to factor the left side of that dotted line. Okay, so what can I factor out of there? It looks like I can pull out an x squared. Okay, what remains? Looks like I can be x plus 3. Okay. Now the whole point of factor by grouping is to make sure what's in these parentheses are the same. Okay. Well, what can I factor out of the right side that would make something beginning in parentheses being x plus 3. Well, I can factor out a, or it would be n. I can factor out n. No, it would be an a, sorry. I would factor out a negative 1. And what remains, if I factor out negative 1 out of this, I would get an x plus 3. And now, what's in the parentheses are the exact same, and I'm pretty done now, right? So I can say 0 is equal to, and it would be x squared minus 1 and an x plus 3. And so this means that my x is going to be equal to, x is equal to a negative 3, and x is equal to a plus minus 1. And those are my zeros. Okay. And so let's go ahead and let's go ahead and graph this. And the graph looks nice and neat right here. So let's ask ourselves a question that wasn't asked in the problem, right? So this is a polynomial, a third degree polynomial, so it's odd, so it's going to have a down-up profile, and of course it's a positive x cubed, so it will remain down up. So my end behavior remains the same. From what we've learned in the first few examples. Now my x-intercepts, we have an x at negative 3 and an x at plus or minus 1. And we see that we do indeed have an x-intercept right here at negative 3, right here at negative 1, and right here at positive 1. Okay, so again, it's not necessarily asked yet, but we will get to that. We will get there later on in the section, but we're just going to jump ahead a little bit. All right, so what we do is we say, okay, so the end behavior here is down, up in some form, okay? We had zeros here at positive 3, here at positive 1, and here at negative 1. Oh, shoot, I'm sorry. It's not positive 3, it's negative 3. I don't know why I didn't see that. Sorry. We have zeros here at negative 3, negative 1, and positive 1. And then what we do is, we would just simply connect these dots and go this way. Okay. Now, that's a very rough drawing, but it's not telling the whole story just yet. Okay. So don't jump on board that just yet, because we're still gonna have to talk about multiplicity. But it's just a general idea of what we'll be doing whenever we do draw our graphs here. Okay. All right. Next up, we have this particular problem. Find all zeros here. Alrighty, so kind of the same issue as the previous problem. We don't really have rules, I guess, to factor a fourth degree polynomial. Okay, but instead what we're going to have to do is we're going to have to just go back to the very basics and just do the factoring that we are used to. So let's go ahead and rewrite this problem. We're going to rewrite this as same way we did the previous example. We're going to do f of x. Just rewrite the whole thing. Okay. And before we even begin, what's my end behavior? Well, this 4, it's an even number, so that means the profile is either going to be up, up, or down, down. This negative tells me it's going to be down, down. Okay. Or actually, probably be a lot more precise if I just did down, down, because we don't really know what's happening in the middle here. Okay, so we're just going to put down, down there. Alrighty, so how do we find the zeros? Well, same thing as on the previous page. We're going to change the f of x. We're going to change it to a y. Right, same thing. Right? Y is equal to, well, in order to find the zeros, we have to set y equal to 0. Well, now let's erase the y and put a 0. Okay, and the same as before, we're just going to scooch this over a little bit. Alright, so I don't like this negative in front there, so I'm going to get rid of it. I'm going to multiply both sides by a negative 1, right? Well, 0 times negative 1 is 0, and then it's going to change the sign of everything on the right side here. So we have x to the 4th minus 3x cubed plus 4x squared. Pretty easy stuff. All right, next thing we're going to do is we're going to factor. So what can I factor out of all these? Well, it looks like I can pull out an x squared. x squared, and so I have an x squared minus 3x plus 4, okay? And then I can factor the x squared minus 3x plus 4. That is a perfect square trinomial. Okay, that factors into no, not necessarily. Mainly because for some reason, I don't know why I wrote a 3 there. So obviously I do this for a living. And it's really funny. I just helped a student out that actually just transcribed incorrectly, like I just did there. We had the 4x cubed and had 3x cubed down here for some reason. I don't know why. It happens to the best of us. The x squared minus 4x plus 4, that is a perfect square trinomial, which turns into x minus 2 quantity squared. So this means, did I write that in green? Okay, good. Just make sure. So this means that my zeros are x is equal to 0 and x is equal to 2. Okay, so really quickly, let's just, without even you know, seeing the graph, let's just try to graph it. Okay, using the same thought process I had earlier. Okay, so I know my end behavior was down, down, right? Okay, we'll have a 0 here at 0, and have a 0 here at 2. Okay. All right. So how does this connect? Well, it looks like, I mean, we might could do this and something like that. Okay, it could look something like that. But it could also maybe look something like this, right? I mean, it's my x-intercepts. I mean, I am indeed, you know, I'm touching the x-axis, right? I'm not crossing it, but I'm touching it. All right. And I guess that might be all that we can do about that. But you know, let's just go ahead and let's be wrong and say that it looks something like that. Okay. And let's actually make it a little prettier so I can compare it to the actual graph. All right. So let's say that it is something like that. Okay. So again, I'm intentionally wrong here because I want to make a point. Notice how the actual graph looks like this. Okay, so what's my difference here? Well, obviously, you know, for this and my zeros, I'm gunning right through my zeros, right? I mean, well, why not? On the previous page, I gunned right through my zeros. I had my zero was at -3 and positive -1. I'm gunning through here at -3 and positive -1. I just shot right through the x-axis. All right. Well, why? What's wrong with me shooting through the x-axis here? Okay, because obviously it was wrong. Well, we're going to see why here in a moment. And I promise you, it's easier than you think it is. Hopefully it's next up because I'm really building this up, aren't I? All right, so okay, good. It's next up. Okay, so next up we're talking about the multiplicity. Okay, so the multiplicity is why our function behaves differently on both those problems. Okay, so let's actually go ahead and move this graph up here to just kind of follow along. Okay, so again, example 5, I shot through the x-axis, but on all 3 zeros, honestly, right? Whereas for this, I just touched the x-axis. Okay. Well, again, the multiplicity is the reason why. So the definition of the multiplicity, if r is a 0 of even multiplicity, right? R is basically standing for root, right? Let's see if it actually shows x minus r here. Okay, it doesn't. Okay, so it's giving you, or it's giving us rather, a variable, but you know, I guess that's what I'm here for, right? The r basically is the root, right? X minus r. So let's just talk about it. If we had x minus r, okay, this r is the root, right? Because if it was x minus 3, that means that my root is at x is equal to 3, right? Or in other words, right here, x is equal to r. Okay, so think of it as the root, right? Alrighty. So if R is a zero of even multiplicity, then the graph touches the x-axis and turns around. If R is a zero of odd multiplicity, then the graph crosses the x-axis at R. Okay, so what exactly is multiplicity? Well, I mean, even touches the x-axis and turns around. Odd shoots right through it. It crosses the x-axis at R, or my root. Okay, so let's go back and look. Okay, so multiplicity is going to be the degree of the factor. Okay, so whenever we factor the polynomial, in this particular case, see we factored. Let's do red. This is one factor, and this is another factor. Okay, notice how in both those cases they are of degree 1, right? It's an implied one, but they're of degree 1. So the 0 associated with this degree is a plus and minus 1 right here. So that means we're going to shoot through the x-axis at my roots plus and minus 1. Right here, okay, it's also a degree 1, and we will shoot through that root at x equals negative 3, in which we did here. This example, notice how this factor is even, and this factor is also even. Okay, well, the x equals 0 corresponds with the x squared, so it's an even multiplicity, so we just simply touch the x-axis and turn around. X minus 2 is also an even multiplicity with the root at 2, so we touch the x-axis and turn around. Both cases, we just touch the x-axis and we turn around. Okay, so let's talk more about that with the next example. So example 7 has it nice and neatly done up for us in terms of factoring. Alrighty, so just looking at this, let's talk about the end behavior first. Okay, so end behavior, EB. Okay, so the end behavior. Well, what degree is this polynomial? Well, looking at the function, we see, you know, well, that's not my laser. The 1/2, obviously, you know, it does not have any sort of variable attached with it, so we don't care about that. This x plus 1 is a first degree, and the 2x minus 3 is a second degree. So we do 1 degree plus 2 degree is a third degree polynomial. So that means my end behavior is going to be down, up. Okay, and since it's a positive, I don't have to flip these to up, down. So that's my end behavior. Now again, let's go back and, I don't think we have to. Okay, so what are my x-intercepts? Okay, so my x-intercepts are, again, we don't really care, the 1/2 doesn't really matter, but x plus 1 tells me that we have an x-intercept here at negative 1, and the 2x plus 3 tells me that we have an x-intercept at x equals 3/2. Okay, so my x-intercepts are at 1 and at 3/2. So let's just, for the sake of it, let's just go ahead and let's draw the graph before we even look at the picture. Okay, so I know that my end behavior looks something like, this. I know that I have a 0 here at negative 1. And I know I have a 0 here at a positive 3/2, so positive 1.5, right? Nothing exact. Alrighty. Well, looking at this particular graph, all right, what is my multiplicity at those zeros? Okay, well, my x equals negative 1, okay, that corresponds with this term there, x plus 1, and it's raised to the 1, but it raised to the first power. So let's actually do this. Just to really avoid any sort of confusion here. Let's rewrite the function. Okay, I'm going to rewrite the function, but we're going to put the power of the factor. Okay, so looking at this term here, x plus 1. Okay, its root is at -1, which was this one, and it is a it's an odd multiplicity. Okay, if it's odd, that means we're going to shoot right through the graph. Okay, so we're going to shoot through the graph. All right, not necessarily concerned with where we're at in the y-axis or anything just yet. So it's actually, yeah, that'll be fine. Okay. Next up, we're going to look at this factor. Okay, that factor, 2x minus 3 quantity squared, gave us a 0 at 3/2, which we see right here. Okay, so it gives us a 0 at 3/2. Well, it is an even multiplicity. Okay, well, an even multiplicity means that what we're going to do is we're going to touch the x-axis and then turn away. And probably shouldn't make it as, there we go, something like that. All right, and that's what my graph looks like. And that's what multiplicities are, right? The multiplicity tells us if we are going to cross the x-axis or if we're just going to touch the x-axis. And since we have an odd number associated with the root at -1, we crossed. And since we have an even number associated with the root here at 3/2, we touched and just took off the other way. Okay. So that's their multiplicity. Now let's give you the better graph version. There it is. And of course, yeah, the better graph there. Alrighty. Next up, we're going to talk about the intermediate value theorem. The intermediate value theorem, it's going to seem like common sense, and it honestly is. It is common sense. But I remember using it, especially in word problems and calculus. I can't really tell you right off the bat what kind, but the whole point of the intermediate value theorem is that you might not know exactly what the 0 is. You just know that there is a 0 between them. Okay, so I feel myself rambling, so let me go ahead and snip this and then describe it. Actually, probably should have done this first. Okay, so concept time. Alrighty, so let's just look at this graph right here. 1 second. All right, sorry about that. All right, so let's look at this graph right here. We have some function. Doesn't matter what it is. It's just some line. Okay. Alrighty, so if f of a, all right, so this is a on the x-axis. This is b. Okay, it could be a 2. This could be a 3. All right, well, 2 and 3 is used for example. Yeah, we'll use 2 and 3. Okay, this can be a 2 right here, and this can be a 3. Okay, if we take f of 2, we see that right here, right? If we took f of 2 and we evaluate the function and it's less than 0, right? If it's a negative number, and then if we took f of 3 and it is a positive number, then that tells me that there is some number between 2 and 3 that has a root at c. All right, if one number is negative, one number is positive, then obviously going from a negative number to a positive number, you have to cross over 0, right? So that tells me that there's going to be some number in there that is equal to 0. And that's all the intermediate value theorem tells us. All right, it doesn't tell us what the number is. It just tells us that there is one. It exists. All right, and that's a lot of what math has to talk about is, something exists. So let's go ahead and show that the polynomial function has a 0 between them. So what we're going to do is we're going to take f of 2, right, because it's wanting us to show that there's a number between 2 and 3. We're going to take f of 2 and f of 3. Now, in order to show it, one of these numbers is, when I evaluate it, it's going to be positive, and one of them is going to be negative. So f of 2 is going to be 2 cubed minus 2 times 2 minus 5, and then f of 3 is 3 cubed minus 2 times 3 minus 5. Okay. So 2 cubed, that's 8. And then 8 minus 4 is a 4. And then 4 minus 5 is a negative 1. Okay, so we got a negative 1 here. And then f of 3, well, 3 cubed is a 27 minus 6 minus 5. So 27 minus 11 is 16. Okay, so since this number is a negative and this number is a positive, I know that there is some number in between 2 and 3, 2 point something, that is equal to 0, right? F of 2 point whatever is equal to 0. And that's really all the intermediate value theorem tells us. It doesn't tell us what it is, it just tells us that it's there. Okay? And let's take off those circles there. All right, turning points. So turning points of a graph is by far the easiest concept that we've done today. And it basically boils down to, and it does bold it for us, right? I mean, obviously this is all in the textbook. You're more than welcome to read all this if you want to. But the whole point of turning points, right? So what is a turning point, right? Well, a turning point is what it sounds like, right? It's where the graph turns. Okay, so where would a graph turn? Not where would a graph turn, but we have a turning point here, 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 and here. Okay, it looks like there's 4 turning points for this polynomial right here. Right? Well, it's kind of the same thing with the intermediate value theorem. We have an idea of how many turning points we have. We just don't know how many. Right? The idea is this bold point here. If f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points, right? So if we have a 5th degree polynomial, which we do right here, it will have at most n minus 1 or 5 minus 1 turning points. So it will have at most 4 turning points. It doesn't mean that there will be 4. It just means that there will be at most 4, right? If we have a 16th degree polynomial, then it will have at most 15 turning points. And that's all we know. We can't tell you how many turning points there are. We just know that we have the at most, right? Okay, so next up, we're going to talk about a strategy for graphing polynomial functions. Now this is the part where we put it all together, and we'll just snip all this to it. And we'll put all these concepts together. It seems like a lot. You know what? It kind of is. I'm not even gonna lie to you. It's a lot. But if we have some polynomial, okay, what we'll do is we'll use the leading coefficient test to determine the end behavior. Next, we'll find the X-intercepts, and then at that point we can talk about the multiplicities. We can find the Y-intercepts and graph those, and of course we have our we can use our symmetry if we need to, that we learned before with our transformations, and then of course we can use the factor of the maximum number of turning points. And it says to check whether it is drawn correctly. And again, we have an idea of how many turning points we are allowed to have. We don't necessarily know how many turning points we will have. So that's a little ambiguous there, but I mean it is what it is. Okay, so let's go ahead and finish off today's lecture with graphing a polynomial. Okay, so all we are tasked to do here is graph this particular polynomial. Okay, but obviously there's a lot to it. So we need to know a couple of things here. We need to get our X-intercepts, our Y-intercepts. We need to know our multiplicities. And again, turning points is kind of I mean, I think the turning points will just kind of come to you especially when you know your multiplicities. Okay, so starting off, let's go ahead and draw our plane here. Okay, so drawing the plane, looking at this particular, yeah, well, let me make that a little bit longer. Okay. Alrighty. So looking at this particular graph, we see that, all right, what degree polynomial is this? Well, let me rewrite this over here just so I can really flesh this out. Okay. So looking at this particular polynomial, what degree polynomial is it? Okay. Well, we're going to look at all three of these terms to figure it out. Okay. Well, the first term, there's no variable involved, so we don't really care about that right now. Okay. Well, this factor is a second degree, it's raised to second degree, and this factor is raised to the first degree, right? It's an implied one. So 2 plus 1 is 3. So this is a third degree polynomial. Okay, so third degree polynomials have the end behavior of down up. Okay, well, notice how it's a negative. So we're going to flip it from down up to up down. Okay, so it's going to be up, down. All right, so there's that. Next, we're going to get our X-intercepts. Okay, well, it's already nice and neatly factored out for us. All right, so what are our X-intercepts? Well, our X-intercepts are at X is equal to, it's going to be a positive 1 and a negative 2. Okay, so I have X-intercepts at positive 1 and negative 2. So again, it's nothing precise. Positive 1, negative 2, like so. Alrighty. Next up, let's talk about the multiplicity. Alrighty, so looking at this factor first, x minus 1 squared. Okay, so if it's squared, well, then that means that we are just going to be touching the x-intercept at 1. This is an x plus 2, and it's raised again to the first power there, so we are crossing the x-axis. Okay, so by connecting these dots, all right, we're going to be crossing the x-axis at negative 2, okay, and then we're going to go down somewhere, and then we're going to touch the x-axis at positive 1, and then we're going to shoot back down. Okay, well now we got to figure out, where exactly do we cross on the y-axis? Okay, well, that's where we figure out our y-intercepts. Okay, so let's go ahead and we'll do this, and we know that we're going to touch something like that. Okay, well, where do we cross at the y-axis? Well, in order to figure that out, we have to plug 0 in for x. So let's do some mental math here. So if you have a 0 here, 0 minus 1 is negative 1. Negative 1 squared is a 1. 0 minus 2 is a 2. And then we have a 1 times a 2 here. So it's a 1 times a 2. And then times this negative 2 out here, right? Negative 2. So negative 2 times 1 times 2 is a negative 4. All right, so all I do is plug in 0 for x. Again, 0, 0, and solved. Right? So I have a y-intercept at negative 4. Okay, so that's, again, just eyeballing it somewhere down here. And that's it. We just connect these dots. And my graph looks something like this. Okay, and of course we can get a better version of it, like so. And that's our function. Okay. So we did cover a lot today. I think it's new things that you might not have seen in high school. At least I don't remember talking about multiplicities and end behavior in high school. Y'all might have, but I think it's a newer concept for y'all. Watch this video some more. If you're struggling with it, shoot me an email. But that does conclude today's lecture.